Welcome students. We want to discuss about tangent plane and linear approximation. Before we start with the discussion, let's read the following quote by William Thurston. William Thurston was a well-known American mathematician. He lived from 1946 to 2012. He has a lot of contribution in low-dimensional topology and three-dimensional manifolds, and he was a winner of Fields Medalist. So Fields Medal is a medal. It's an award you get. It's equivalent to a Nobel Prize in mathematics, except for the fact that it's awarded every 4 years. So, tangent plane and linear approximation. So recall, partial derivatives are essentially slope of certain curves. So consider the following function. So you have, let's discuss the setup. So you have z equals to f of xy, and you have a point PAB on the surface S defined by z equals to f of xy. So S is a surface defined by z equals to f of xy. Consider A, B, C, P on surface. This clearly means that since it lies on the surface, it satisfies the equation of surface. So you have to this. So you have C equals to. Now, in partial derivatives, what we did was we fixed one of the variables. So let's fix, for example, so let's fix x equals to a. So fix x equals to a. So if you fix x equals to a, we are, so along this line, your x equals to a is fixed. And if you look at x equals to a, it's a plane. So when you extend this plane, it will cut your surface in a curve. So let's call that curve as C2. So at point PABC, we will have tangent line to this curves. Let's call that line, tangent line, as T2. We do the same thing. So now what is the slope of this tangent line? So slope of tangent line to curve C2 at P is, so you are fixing x equals to a. So x equals to a is fixed, and you're seeing the change in y. And if you recall, that is partial derivative of f at a. Similar argument basically tells us that if you fix y equals to b, then you get curve. So let's use a different color pen to signify that. You get a curve C1, and tangent to that curve C1 is T1, and the slope of T1 is partial derivative of f with respect to x. So if we take a plane which contains both T1 and T2, these tangent lines at P, then that plane is called tangent plane at point P to the surface S. Okay, so that is the definition of your tangent plane. That is one of the definitions of your tangent plane. You could also basically think about all the vectors whose initial point are at P, and that span this, and all our tangent to this surface basically give us the collection of all those tangent vectors, give us the tangent plane. All right. So now we want to basically, if you want to look at the graph of this, this is how the tangent plane looks like. You are at point, so this is your A, B, 0. This is your surface S, which is given by f of xy. And this point is P. And this plane here is the tangent plane at P. Now to find out equation of plane, we need two things. So tangent plane is after all also a plane. So we need two things. Find the tangent plane at P. We need a point. So the point is already given to us, P, which is given by A, B, C, or we can write it A, B, f of A, B. Now we need normal to the plane. That will be basically cross product. So basically we want normal to T1 and T2. So we can get that by cross product in the following way. So first of all, we'll take these two curves. So first curve is, so take the curve where you fix x equals to a. Okay, so then we get, so let's start, fix x equals to a. In that case, z is f of ay, and we get this curve, gives curve C2. So this curve here is curve C2. Now, what is the vector equation of this curve? So equation of C2 is, let's call it as R2 of y. We can choose to parameterize it by y. X is a fixed, y is y, and your z coordinate is f of a comma y. So therefore, direction of tangent line to C2 at P is, so we want to find out the direction of this line. The idea is we'll find the direction of this guy, we'll find the direction of this guy, we'll take a cross product. So we want to find out direction of these T1 and T2. So direction of tangent line to curve at P is R prime, R2 prime, but instead of Y, you are evaluating it at what point? You're evaluating it at B. That is going to be, so derivative of this is 0 with respect to Y. Derivative of this with respect to Y is 1. Derivative of this is A, and then you're substituting Y equals to B. So that is going to be 0, 1, AB. Similarly, equation of C1. So what is C1? C1 is this curve when you fix, so when you fix your y equals to b, then you get curve C1. So this is your C1. So let's find out the equation of curve C1 is R1 of x. The first coordinate is x, which is changing. Y coordinate is b. So we fix y equals to b, isn't it? Along this line here, we have y equals to b. Along this line, we had x equals to a. So let's just label those things. So we get this is f of y is fixed b and x is changing, and therefore direction of t1 is r prime of x. Now the derivative is happening with respect to x, so that is the variable. We have 1, 0 partial derivative of x with respect to this, and you are evaluating this at a. So a, which is same as b, and then you substitute x equals to a, and that is given by 1, 0. So the normal is, you can take either way. I'm going to take R1 cross with, so when I take cross product of these two vectors, so I can take normal to be, let me take normal to be this guy. So cross product of this will be T2 cross T1. Let's take that right hand rule, although it doesn't matter. So T2 cross T1 is going to be, so let's just rewrite it in slightly different format. And if I take cross product of this vector and this vector, we'll see that that is going to be, it is going to be, you can check that it's going to be AB, AB, and 1. Therefore, equation of tangent plane, now we have a point, we have a line, so equation of tangent plane is, take this normal, so dot with the x minus a, y minus b, z minus f of ab, this dot product is 0. Okay, so now when we simplify this, we get, when we multiply it out, we get minus of dou f by dou x of AB times x minus a. So let's keep this in a big bracket. My plus minus of dou f by dou y of AB times y minus b plus z minus f of AB times 1 equals to 0. And if you bring these two things on the other side, you will get the following equation. of your tangent plane. So now we have found out the equation of tangent plane to the curve z equals to to the surface z equals to f of xy at point P, which consists of a, b, f of a. So now let's apply this new formula we have. So find the equation of the tangent plane to the curve at point 1, minus 1, 1. So first we need to compute this guy at 1, minus 1, right? We need to compute this. So first we'll compute the partial derivatives. So this is going to be, now you want to apply the derivative, so you have to apply, so derivative of square root of x is 1 by 2 root x. So this is going to be 2, 4 minus x square multiplied by derivative of inside, which is minus 4. Derivative of 4 is 0. Derivative of minus x square is minus 2x, and derivative of minus 2y square with respect to x is 0. So this implies partial derivative at 1 minus 1 is going to be 1 upon 2 square root of 4 minus x square minus y square. It's already computed here. It turns out to be 1, right? This is equal to, when x equals to 1, y equals to minus 1, then z equals to 1, right? So I have already, this computation is already done for you here, so you don't have to substitute it, but if you wish, you can. Let me just write it down anyway. So 4 minus 1 square minus 2 times minus 1 square multiplied by minus 2x. And this will give us minus 2 times, our x is also 1. So this will give us minus 2 over 2, which is minus 1. Now let's compute the y. Again, same thing, apply the chain rule multiplied by derivative of inside, which is going to be minus 4y. This gives us at 1 minus 1 is going to be 1 over 2 times minus 4 times minus 1, which is going to be 2. So therefore, equation of tangent plane is, let's go back here, is z minus f of ab. So let's write out the equation for once. Is going to be z minus f of ab, or in this case, since we are calling it as z itself, we are not using f, so it's going to be z minus z of 1 minus 1. Note z is a function of x and y, so that's why I can write it like this, equals to partial derivative of z with respect to x, however evaluated at 1 minus 1 times x minus a, which is 1, plus 1 minus 1 times y minus of minus 1 plus 1. So this gives me the equation of plane is z minus 1 equals to, this is already computed to be minus 1 times x minus 1 plus 2 times y plus 1. So this is our equation of the tangent plane here. Okay. So now comes the concept of linearization. So ZBF of xy has continuous partial derivative at point AB. The linear function whose graph is tangent to the plane at point P is called the linearization. So what kind of graph? So first of all, note that this is a linear function, right? So why is that? Because its power of x and power of y are both 1. And if you look at the linearization of function at AB, it represents the tangent plane, right? Because the equation is given by z minus f of AB equals to fx AB x minus a plus fy AB y minus b. And then you bring this guy on the other side, and then that z, so this z represents all the points, like the z coordinates of the points on the tangent plane, right? You're no longer in the surface. So this is called the linearization function. And if you use this linearization function, you get what is called a linear approximation. So recall, in function of one variable, if you had to do linear approximation at a, you basically drew the tangent line, and instead of having x, so this was the f of x, and this point on top on your tangent line was L of x. Linear approximation for f of x. So same thing we are doing here as well, that instead of finding the value of the function, say if I take xy, which is close to this, instead of finding the value of the function on the surface here, I will find the value on the tangent plane. That is called as a linear approximation in two variables. So this is a formula for linear approximation. So this is essentially your L of xy. And if you're approximating your function by the values on the tangent plane, you get linear approximation. So let's work on a problem. So let f of xy be x e to the power xy. Use linear approximation to find out value of f of 1.01 minus 0.03. All right. So first we need to take a point, a nice point, which lies on this curve. So let's take x can be taken to be, so if we see, we can take a is ab to be 1 comma 0. So in that case, we need to compute the partial derivative of this with respect to x first. This is going to be x, product rule. So x times e to the power xy multiplied by derivative of e xy, which is y, plus e to the x times, so e to the xy times derivative of x, which is 1. So this means this evaluation at 1, 0 is going to be, so this will disappear. You will get e to the power 0, which is 1. Similarly, if we look at partial derivative with respect to y, we have x is a constant with respect to that. So e to the power xy times x, and that is going to be giving us partial derivative at 1, 0 is going to be again 1. So therefore, linearization function at 1, 0 is f of 1, 0 plus partial derivative of x at 1, 0 times x minus 1 plus partial derivative of y at 1, 0 times y minus 0, right? So this is a linearization formula if you see from here. Okay. And if I simplify this, so this is my, I'll have notation for this. This is already L of xy. And if you simplify this, this is going to be f of 1, 0. So if you put 1, 0, so you get 1 plus, this was already computed to be 1. So 1 times x minus 1 plus y, which is same as x plus y. So this is a linearization. So what is f of 1.01 minus 0.03 is going to be 1.01 minus 0.03, which is going to be 0.98. So this is your linearization. So I should write it down. I should write down the intermediate steps. So I should say that my L of this is roughly equal to my f of our f of 1.01 minus 0.3. This is roughly equal to this value because of our linearization, and we get that value to be 0.98. All right, okay, so now let's talk about increment. So we want to see, again, we want to measure the following. If there's a change in the function input x and y, if that changes, how much does your function changes? Okay, so namely, if your x changes from a to a plus delta x and y changes from b to b plus delta y, how much did your z change? Well, clearly, that is can be written as delta z equals to delta of f of xy, which is f of x plus delta x. Actually, it should be a plus delta a. Oh, well, in this case, our x is a. So it should be a plus delta x, b plus delta y minus f of ab. So this gives us the change in your function if your x changes from a to a plus delta x and y changes from b to delta y. So this leads to the definition of differentiability. So in two variables, so we say z equals to f of xy is differentiable if delta z can be expressed in the form fx of ab plus fy of ab delta y plus epsilon delta x plus epsilon delta y, where epsilon 1 and epsilon 2 go to 0, both of them, as delta x comma delta y go to 0, 0. So what does it mean? It means that a function is differentiable if the linear approximation is a good approximation for the function, right? So this is what it means by function being differentiable. So in some sense, if you look at the following function, so if you look at the following surface, which is given by some kind of a cone structure, if you draw a tangent line here at this point, it is not a good approximation for function value at other points, right? So if you look at a function value here, this is a function value, this is the approximated value. If you go nearer to this point P, which is A, B, C, this point is A, B, comma 0. Any point here, if you're looking at the linear approximation, will lie here. So let me just draw those things properly. So if this is my function, which is this pyramid with the bottom removed, of course, otherwise it won't be a function. If I'm at AB, if I'm trying to approximate this value, this is actual value of the function, actual value. And if I'm trying to approximate it by tangent value, it's quite far. Yeah, at least that's what it looks from the graph. So this is not differentiable at this point. Okay. So that's the idea behind the differentiability. So how do you see that a function is differentiable? This is an important theorem. You will explore more of it in math 322. If the partial derivatives fx and fy exist near AB and they both are continuous at AB, then f is differentiable at AB. So this is a very interesting result. You will see the application of this when you're doing math 322, all right? And okay, so right. So note there are a few things about differentiability which is different. So here there are quite a few concepts of derivative, right? One is the partial derivative with respect to x, partial derivative with respect to y. Now one should ask, what is the connection of being differentiable and these two partial derivatives? So this is what the theorem says. If you take these partial derivatives fx and fy, and if they exist near AB and are continuous at AB, then f is differentiable at AB. So you see these partial derivatives, the continuity of them around AB give the differentiability of AB. That means the tangent plane is a good enough approximation, yeah, or the increment can be approximated by the linear approximation. They are all same things. Anyway, so there's few warning here, namely, first, a function of two variables is differentiable at AB if it can be approximated sufficiently close near AB by a linear function, that is geometrically by tangent plane. This is what I said. Let's be just repeating it. Another thing is the following. The theorem implies that if partial derivatives are continuous, then f is differentiable. If f is differentiable at that point, then the partial derivative exists there. However, if the partial derivatives both exist at a point, that does not guarantee the function is differentiable. Forget about differentiability. It does not even guarantee that the function is continuous, right? So the existence of partial derivative does not tells you the existence of the derivative, right? Yeah, I mean, so now we want to talk about the concept of differential. So again, recall what was your differential. So you had a function of one variable. So you have a point A, you have a tangent line at A. So suppose your function changed from A to A plus delta x. Yeah, then your y value changes to, this is your delta y, which is f of A plus delta x. And what your differential was in this case was the change in your tangent line. This was your dy. Yeah. So instead of taking the change in the function, you change the change in the tangent approximation or the tangent line. That gave you dy, and it is given by f prime x, because rise over run, this is your dx over dy equals to f prime y x. So we get f prime x equals to dy by dx, or we got f prime x dx equals to dy. So this was your differential. We want to have a similar concept of differential in function of two variables. One may ask why. Well, you want to see how much does your change in the function happens, which is delta y, but you want a good approximation for it, which is easy to compute, and hence you took dy. And also it tells you about the results about differentiability and linear approximation. Okay, so let's repeat that here. So again, we start with a point AB, comma 0, A comma B comma 0. We let A change to A. So we change in A, we change A plus delta x, and Y we do b plus delta y. So if this is delta x and this is delta y, then you reach to this point, a plus delta x, b plus delta y is 0. Now, what is the function value on top of AB is this point here. What is the function at a plus delta x, b plus delta y is going to be this value. So this corresponds to, so corresponding to this value here. So how much did your function change? Your function change from this value up to this value. Since we are looking at the 3D perspective, all these in this box, all these horizontal, at these points, all the values of y are same. So your function changes from here to this point here, right? And this can be seen as delta z, which is going to be, so what is your delta z? Delta z is essentially, delta z is the new value of function calculated, f of a plus delta z, b plus delta y minus f of a, b. So this is your change in the function, and you want to approximate it by how much did your change in tangent line happen, and we call this as dz. So how much did change in z happen? So change in z, if you look at the result, we have the equation of tangent plane is z minus f of ab, which is fx ab times x minus a, fy ab times y minus b. So how much did change in y happen? Sorry, change in z. The change in z was exactly z minus f of ab, right? This was your original value. And since this z signifies the value on the tangent plane, z minus f of ab gives you the dz. So we get dz equals to fx of ab, ay times delta x plus fy of xy delta y. So this gives us the differential. Okay. Now so this is a differential of this function. However, differential at AB, the differential at AB is given by dz. Well, you can call it dz at AB. That is given by dz evaluated at AB times dx, dz evaluated at AB. Or in this notation, I can write it as fx of AB delta x plus fy of fy of xy delta. Okay. So let's do this computation now. So let for f of xy equals to this function, calculate f of pi by 2, 0, and the differential approximate this value. So let's work on this. So how would we go about it? First of all, what is f of pi by 2 comma 0? This is going to be 2 sine pi by 2 plus 3 cos 0, and that is going to be 2 plus 3, which is 5. Now, delta z is the approximation for your function. So this is your f of 29 pi 60 pi by 50 time minus f of pi by 2 comma 0. Now this guy, this is what we want to compute, and this guy can be approximated by dz. Again, dz at what? 29 pi by 60 pi by 50. Okay, so this is what we have. Once we find the approximation for the delta z, which is the increment, we can find out the thing. Now, what about this as a formula? This is given by with respect to x at 29 at AB, right? At AB, your AB is pi by 2, comma 0. So at pi by 2, comma 0 times x minus the new value 29 pi by 60 plus evaluate pi by 2, comma 0 times x minus pi by 50. And so let's compute this first. So we have, this is going to be, when you evaluate, take derivative with respect to x, you get 2 cos x, and derivative with respect to y is going to be, derivative with respect to y is going to be equal to minus 3 sine y. So this implies dou x at pi by 2, comma 0 is 0. Cos of 0, which is, sorry, cos of pi by 2. Let's write that step down. So it's going to be 2 cos of pi by 2, which is 0. Similarly, at pi by 2, comma 0 is going to be minus 3 sine 0, which is 0. So in this case, what we get is delta z is approximately equal to dz, which is 0 times x minus 2, 29 pi by 60 plus 0 times x minus 50, pi by 50. So in this case, we got delta z to be 0. And that means, this means what? This means the linear approximation for f of 29 pi by 60 pi by 50. So this is 0, means that this guy is 0. And this would lead us to f of 29 pi by 60 comma pi by 50 is equal to f of pi by 2 comma 0, which was 5. So this is a linear approximation for this. All right, so we can play the similar game or process in function of 3 variables. So let's w be function of 3 variables, x, y, and z. The linear approximation is given by f of x, y, z is fxy of ab times x minus a, fy of abc minus y minus b, fz of abc, z minus c, plus f of abc. Now note that this will not represent a tangent plane. All right, it represents a entirely different object. All right, so it's hard to visualize 4 dimensions. But nevertheless, we can do these linear approximations there. We can do the increment as well, which is f of x plus delta x, f of y plus delta y, f of z plus delta z minus f of x, y, z. Differential is given by the following, and yeah, okay. So this is the setup. All right. So again, we have to be, so this is in terms of x. If I have to write it in terms of a, I should write a, b, c, a, b, c. And here, when I write differential, differential at ABC, then I should evaluate these guys at ABC, evaluate this guy at ABC, evaluate this partial derivative at ABC. Okay, so let's look at the following problem. The dimension of a closed rectangular box are measured as 80 centimeters, 60 centimeter, and 50 centimeter respectively, with a possible error of 0.2 centimeter in each dimension. So we have delta x is going to be 0.2, delta y to be 0.2, delta z to be 0.2. So this is what we have. So in fact, we have, if we take the absolute value of this guy, this has to be less than equal to this, less than equal to this, and delta z is going to be less than equal to this. So these are the maximum possible errors. All right, so we should take, so to make sense of things, we should take dr, then in that case to be 0.2, dy to be 0.2, and dz to be 0.2. So these are the possible, the largest change in x, y, and z. Now, so what is given to us? We want to estimate the maximum error in calculating the surface area. So what is the surface area of the box? So if you recall the box, if we take the box whose dimensions are x, y, and z, so this is your x, then we have, this is the y, and if the z is this, then the surface area is given by, so surface area S of x, y, z, surface area. Its surface consists of 6 rectangles. So the first frontal rectangle has as area xz, so it's going to be 2xz. Similarly, if you look at the side rectangle here, it's going to be 2yz. This one and this one is 2 y. So now, what is the maximum error possible? So maximum error possible is delta S, which is then approximated by ds, which is nothing but. So now we are evaluating this at 80, 60, and 50. So x equals to 80, y equals, so we have a, b, c. So we have at 80, 60, 50, this is going to be, so your delta S is approximately equal to the differential ds, which is going to be partial derivative of S with respect to x, evaluated at 80, 60, 50. Similarly, y times dx, this 80, 60, 50 times dy plus dz, 80, 60, and 50 dz. So this is the differential. Of course, we'll put the values of dx, dy, and dz later. So let's compute these things. So we have partial derivative of s with respect to x. So if we take with respect to x, we get 2z, this will become 0, and this will be 2y. So 2x plus y. Now, because of symmetry, you can argue that this is going to be 2x plus z, and we have 2 x plus y. So now we get, so therefore delta s, which is roughly equal to ds, is going to be 2 times x plus y. So x is 80 plus 60 times dx, which is 0.2. So they all have the same thing. So dx, right? Plus 2 x plus z. So it's going to be, so hold on. This is x plus, so there is an error here, namely, if you take the derivative, it's going to be 2 dx is going to be, when you take derivative with respect to x, you get z, and then you get y. So z plus y, right? Okay, so that's an error. Good that I caught it here. So here we get z plus y, which is going to be 60 plus 50. Then the next one is going to be 2 times x plus z, 80 plus 50, plus 2 times x plus y, which is 80 plus 60 times 0.2. And if we simplify this, we get 2 times, we'll take 2 common. I'll take 2 times 0.2 common out of all of this. I have 2, so I'll have another 2 coming. So, or I can multiply it out. So I can add this, becomes 110 plus 130 plus 140, 120, 140. That's right. So this becomes 4 times, so multiplied out, you get 4 times 11 plus 13 plus 14, and that is going to be, so it's going to be 152. That is a maximum error, 152 centimeter. So this is the idea behind the differential. So this is the error, maximum error, which can creep in while calculating the surface area. Thank you for your attention.